Hello everybody, thank you for attending. Today I'll be talking about automation with MIDAS Civil, what I have done and what tools I have developed to work with MIDAS Civil. I'll be talking about what can be done and what has been done with the previous versions of MIDAS Civil. The session will be divided into two parts. Essentially, the first part, pre-API, or what some might call semi-automation, where I'll talk about my approach to the API, to automation with MIDAS Civil and generally automation, some tools that I've developed to use with MIDAS, and some early examples of automation, or essentially semi-automation. The next parts I'll show some examples using Civil NX and the API, and some of the tools developed to work in conjunction with the API itself. So moving on to the first the first session, the general idea is of what automation could be done without MIDAS Civil NX. So the previous version of MIDAS Civil, and the tools that I've used in conjunction with that. So basically, my philosophy with automation is that you should be able to do one bridge, one engineer, one day. This is of course for standard typical bridges. So typical overpasses, underpasses, culverts, PSC beam bridges, various types of standard bridges. Essentially, if you have more than a couple of bridges, standardization should be possible. Standardization and automation. So for typical bridges, this is more than enough. With the new M collection, this is now all possible within one family of software. So in this case, MIDAS Sim plus MIDAS Civil work really great together. And it's just creating the scripts that will then interact with each of the programs. Today I'll be concentrating on MIDAS Civil itself. No, I won't be talking about MIDAS Sim. That would be a next step process. First of all, when we start developing tools, we should basically have know our expectations from automation. One important thing that I see very often as a problem is we should well define what we expect from the automation. We can't create a tool that would have every single use case, edge case, and at a certain point we have to do a cutoff. If we have a big project within which we have 20 various bridges, and one of them is significantly different from the others. It might also be, for example, pre-stressed concrete beam bridge, but it might be with a totally different geometry, non-standard to the rest. The question is, should we then spend the time to include that edge case, or do we not include it into the automation and help develop the tool quicker? The idea for automation essentially is who would be the user then. Will it be a standard engineer, or an engineer with programming skills, Grasshopper, or any other programming skills? Or do we want to base it on an average engineer that just understands basic Excel spreadsheets? Ease of use and aesthetic interfaces are a high priority for me. If it's not easy to use, if it's difficult and cumbersome, none of the engineers will want to use this. Senior engineers won't understand the program, won't want to implement it, so there'll be they won't want to use it. That brings me to the next issue of trust and internal verification. Nobody will want to implement a tool if there's no level of trust of what has been done. One of the good things is MIDAS Civil NX is a good base for this trust. If you were to write your own program, your own MES solver, or FEM solver, you wouldn't have that trust. So using a ready tool such as MIDAS with the API is very beneficial. And then the results and conclusions are basically based on standard practices within the office. And then internal elasticity of such a script or program is a must. If you move on to a new project and you have to redo all your work just because there's something slightly different, it means that you're wasting a lot of your time. So with that in mind, my methodology is basically to use these three points that I show here. So Civil NX and external tool. The external, in my case, I use Python programming, and what I essentially do is all the different tools that I develop are bricks that can be stacked together within a bigger program to create the bigger program, and that way I have the elasticity to interchange these things. For example, if within a new project, instead of having pre-stressed concrete beams in the bridge, instead of that I had steel girders, I could very easily interchange that one section regarding the composite steel elements, beams, and everything else would be the same, and I wouldn't have to change that much. And they should be able to work independently of the whole, but also be able to be used within the whole program. So like with the standard brick, you can either build a wall, a home, or a tower. The choice is up to you what you want to build, but you have the tools to build it. So one of the main things I did earlier was develop a library called MIDAS Export, basically to simplify creation of models within Python. The idea making it more Python-like, Python-esque. So here, just a simple example showing of within the model, just adding the Euro codes, adding a line lane. So this would be the track with the various offsets and elements to which it's applied. Then adding the train loads LM71, and then the moving load case, and then adding combinations. The same with dynamic analysis. The idea was to simplify everything. So essentially here I can add one of the HSLM trains. This could be of course done in a loop to add all of them at once. The minimum and maximum speeds, and then the step between each of the speeds, and then which nodes are loaded and so on. With the previous version of MIDAS Civil, this was somewhat limited, where the script would only go in one direction. So you could only export to the model, but you couldn't get information back. Now with the NX, this is possible in both directions. Another one of the external, now some of the external tools that I also developed were for example for calculation reports. Basically I used a Python library. I created a Python library using that uses LaTeX and the LaTeX scripting language to generate PDF reports. Here's a couple of examples of what is generated within the reports. Here's a W-beam used. The different colors signify internal or external surfaces within the beam. These are all the tendons within the beam. All of this is automated in the Python script. All of this is generated. The idea being to make it as simple as possible and to separate creating all of your elements, your calculation reports, from the formatting that is done within the calculation report. So one of the tools within bricks within that other brick essentially would be creating a spell check, which I use Jupyter notebooks here to write all of the code. Whatever is shown here, I have the option to turn off, to show or not show what it would look like within the calculation report. With a built-in spell check, and it highlights in red the things that are misspelled. Of course, at this point, these are just references, but if one of the words were to be misspelled, it would just be shown in red. So I can then change this, update, the text would be updated, and then only later when it's exported to the PDF report, this then gets generated. This again, as was seen earlier, the tables look slightly different. That's what is used with a template. So the templates could then be project specific. You could maintain the whole calculation report and only change the graphical representation that is done with the template. So the formatting of the tables, colors, borders within the document. If you want a table of contents, the formatting of the table of contents, font and so on. Another tool that I developed was for reinforced concrete slabs, for the design of them. Essentially, this just gives for each of the directions, so along the line and horizontal to it, perpendicular to it, which angle can be changed. And for the reinforcement at the top and the bottom, it shows a map of the amount of reinforcement shown, required. I'll show a more detailed analysis later, but this was for a curved composite bridge. This was the deck, and this is the reinforcement layout that was required. So basically, early automation without an API essentially was divided into these 5 steps. So you'd create a model, export it to MIDAS, which this would be done by hand through, for example, through an MCT file. You would then have to run the model, export the results then back to a post-processing element, which would be either done by hand or with options within MIDAS to export the results, and then you'd be able to do the post-processing. Now with the MIDAS Civil API, you essentially can get rid of 2 of these points, where within the model creation you could then also directly export the model without having to do anything by hand, and then after running the model you could then import the results back into your post-processing. Later on I'll show an example of this whole process, and one of the examples of pre-automation that I did was for gantry design, where basically we had a large amount of typical steel tube gantries, where this whole model was generated within just a couple of input parameters. Then the MCT file was generated. This had to be then imported within MIDAS, the program run, and then export everything by hand, exported, all the tables generated. Here, as a side note, just 2 models were generated, one with plate elements, one with beam elements, to then compare the 2 results. Also, some design criteria are required for an entire section, while detailed design would then be used in the plate element model. The advantages of this parameters was essentially saving time. Full analysis of a gantry, including the generation of the calculation reports, took 30 to 40 minutes, while the most time-consuming element was the hand export of the results, which would be about 90% of that time. and that's time that is required from the user of actually being there and copying and generating the tables, which is prone to errors. After doing it a couple of times, you might forget a table or two or some elements. Another advantage was basically everything could be a parameter. So here, for example, one of the parameters was the amount of finite elements within the circular tube. Here a very fine mesh, a medium mesh, and a very coarse mesh. Then the results could be done, and then by increasing the amount of elements within the mesh, one could check convergence to a solution and see how far off. At a certain point with this solution came out to be the most optimal. The results were very close to, almost identical to the much finer mesh, but required a lot less time for calculation. And then changing loads. For example, if the gantry was in another part of the country, all that had to be changed was a parameter or two within the initial spreadsheet, and then everything would be updated. Everything was then automated from the report generation and results, and then templates could then be used for a new project where we'd have the same standard design and everything would just pop out. And here is an example of the calculation report that was used. So essentially, all the formulas are populated, all the values are given, everything can be checked, all the values inputted, reference to all of the required norms, all the values that come out, and everything would be then in the calculation report. Easy model verification. So if we know the area of certain elements, for example the wind load in the X direction, I would calculate it, then I'd read from MIDAS Civil the reactions that came out in the model. So in the B model it was exact. Within the plate model there was a slight discrepancy, which was due to when modeling a plate element, you model to the center line of the tube, which gives a slightly less surface area of about 0.5%, which was more or less the difference. But generally all loads could then be verified if they were applied correctly and within required values. Also, while doing this, I developed tools for designing of welds within between steel elements. So this was all detailed to design the weld that was going around the circumference here. The problem with the 45-degree cut here is you don't have a nice clean situation where you could just use a butt weld or just use a fillet weld. This is a weld that is essentially is somewhere between the two types. So here is a plot of the angle around the circumference of the tube, here going from 0 to 360, and then the maximum stresses in different directions, where the sigma max min and the perpendicular stresses, and then later that can be combined into utilization, and at the same time an optimization for the thickness of the weld could be used, where this could be rerun for different thicknesses of the weld and then checked to see what the optimal thickness is for the weld. Everything done within MIDAS Civil and the script here. Another example here for an integrated road, integral road bridge, just to show the benefits of automation, where the thicknesses of each of these elements could then be varied, and very easily the amount of reinforcement could then be calculated and then given and then populated into a spreadsheet to each of the values. Very easy then to calculate the estimated amount of rebar and the amount of concrete applied cost to each unit value, and then calculate with each thickness what the cost of building the bridge would be. And then it was very easy to find an optimal solution for the contractor. And here is an example of the results from the design of the plate. So here different places and elements, regions are shown with the amount of reinforcement, and the value, for example, the value of 37.5 is the amount of square centimeters per meter width of the structure, and it's easy to identify which areas require more reinforcement, which areas require less, concentrations in certain forces, and what can be done further. Essentially from this you could then think about automation and exporting required reinforcement to a MIDAS sim model. Now on to the second session. So now working with the Civil NX and the API. So first, the MIDAS export library. I wanted to show a basic example of how this can be used, how one can be integrated with the other. Then an example of the API in process, and some final thoughts about future developments and how to continue with this. So essentially, the MIDAS export library, some initial questions that I often get asked is, well, why use Python and Jupyter notebooks? For me, it's ease of use and elasticity. This all, of course, could all be done through Grasshopper or other libraries. I started developing this many years ago, so it was easy for me to continue. But it's also a tool that then could be used within other programs. Grasshopper has the option of importing Python code, so it can be used within Grasshopper to make certain elements. Also, many elements can be saved to libraries, like for example material codes, repeatable functions, or for example creating a catalog of pre-stressed concrete beams that would include both the beam, the cross sections, its parameters, and the tendon layouts, the standard tendon layouts. All of this is run in Visual Studio Code in conjunction with Jupyter notebooks. That was shown earlier. Do I use any commercial extensions? No, all of it is based on free-to-use models. So why create my own library and not just use the JSON scripting? First of all, I started developing it earlier before the API came out, but also this allows for a lot of housekeeping to be done in the background. So no need to first define, for example, load groups or construction groups. Everything can just be done in the background. When defining, for example, a load, it can automatically generate a load group. The same with elements and so on. It's also, the code is more Python-esque. And why not use Word or Excel for calculation reports? Well, basically, it's easier to standardize templates and the layouts with such tools and using LaTeX. Generally, it's a scripted language from the very beginning, while Word and Excel have some issues with scripting. So now I want to move on to an example of MIDAS exports using Visual Studio Code. Let me just switch over to MIDAS Civil and Visual Studio. So this is a basic example using the scripting and MIDAS export. So first we basically create a model element, giving it a certain name, and this is the entire code to make a very simple model within MIDAS Civil. I'll just run this code and you'll be able to see how everything works in conjunction with the MIDAS Civil API. Here I forgot to turn on, connect the API. interrupt. My apologies, and rerunning the code. In the meantime, while this is running, basically everything is simplified to make this is essentially a tool for making tools, so everything is simplified here. It's easy to add a material, a cross section with the different parameters. Adding nodes is very easy. The idea here is just to create a spiral with all the elements connecting them. With adding the supports, the load cases, self weights, and the loads. Here the idea is to make it as easy as possible to add loads. So here's a beam load, and it can be applied to a load group directly. And then here construction stages are added, and load combinations as well. Then very simply, you can export the model directly to MIDAS. From the script, save the name of, save the file, run the model, so run the analysis of the model, and then save all the results. And we have a ready result here within MIDAS Civil. Here we can look at the result table, results, so displaying results, forces, beam diagram, and for the load combination, for example, the forces, the axial forces, and apply. Here showing all of the values. Let me just turn off. So these are the values. One of the new things in this Civil NX is now the ease of use. So for presenting all the values, it's much easier. And as we can see, for a simple spiral, we have the values. Calculation time under 1 minute to create, run, save the entire model. And now from this we could then import values, results, displacements, anything we need. As a side note, once something is calculated, you can then export all of the, you can export the model. The advantage of exporting through the JSON files is now that you not only save the model, but you also save the results. So I'll comment this out for now, so it doesn't interrupt us, and back to the presentation. So now a more advanced example of using the API. Here, as I said earlier, I developed a program for PSC beam bridges based on the Type T beams available in Poland. These are standard road bridge pre-stressed concrete beams. They have a very set cross sections and tendon layout, like in most catalogs. All of the information from the catalog essentially was codified here, which was very simple to do. The idea was here to make as few limitations as possible. So the amount of beams in the cross section is not limited. The spacing for each beam can be different. The structure can have one or more spans. And since these are standard loads, and in Poland all bridges have a certain standard amount of certain standard loading, everything can be done by the script and the program. The only essential changes that come up with using the Eurocode is the location, which would change the either wind or temperature loads. But for today's example, I won't be implementing the wind or temperature loads, just so that the calculation time is a lot more bearable. Another side note for Jupyter notebooks is you can have a table of contents and then jump to the important sections that you need within the book, the notebook. So here we would run all of the elements, and jumping over, this is the Excel spreadsheet that shows the basic layout on the top of the structure, what type of cross beams, what type of PSC beams are being used, the height of the various elements, This is the amount of elements along the length of between the cross girders, and essentially the amount of beams, the spacing of the supports, which can be different on each of the supports. This of course could be extended for more elements if needed. The spans and the various loading that is added. I added here a point for the vertical curve within the bridge. This then allows, if we have a beam that is horizontal and it starts at 2 points, it'll be a straight line between those points, but then the roadway can be in a vertical curve, which would cause more concrete in the center of the beam than on the ends of the beam. So here's just an exaggerated example of 100 meters, and to show what that would look like in the model. And then everything here is then exported to MIDAS Civil. So here, just to show the the tendon layout. So the tendon layouts for T27 beams are such. This is then implemented directly to each of the beams, where it takes into account the length of the beam that is actually defined, cuts off from the ends whatever isn't needed, and we have this beam layout. This is then run within the project, within the model. We extract the results and we see if everything is okay, and if we have to amend the amount of tendons in the cross section, or have some sort of elements cut off. Here, just as an example of superimposed dead loads. So the dead loads are then added directly as a pressure loads, the load case that they're added to, and the elements that they are added to, and they are directly added to a load group for construction stages. At this point, I'll just export the model, just so that we can see MIDAS Civil at work. So running all above. As you can see, the model is now resetting for the new, the program is resetting for the new model. Creating a new file, you have to wait generally a little bit. This starts coming in. As you can see, it's slowly being populated. The materials, time-dependent elements applied to materials, the different cross sections, the thicknesses, the thicknesses nodes. Here are all the nodes. The boundary groups now exported. Here the cross sections added. The elements, as you can see, the varying thickness of the model here has been added. Generally a good idea is once this is exporting to not click within the program, just in case. It might interrupt the contact between the two programs. Now all the loads are being passed in, the tendons and tendon groups and tendon loads directly into the model. Now all of the moving loads, the moving cases, moving load cases, the vehicles, the moving load cases, and all the other elements. And this is now a ready model that we can use within Civil NX. Everything is here ready. As you can see, this has been added, a 100 meter vertical curve to these elements. The varying thicknesses here. When it comes to the the amount of elements then changes. There's no limit to the amount of intermediate elements. This could be finer or more coarse. The loads added. So here, for example, the wet concrete that is added, as one can see. The load also varies along the length. Let me just change the view. So it varies across along the length of the beam, but also looking at the cross section. Let me just, if now we were to just limit to a couple of beams, these have different spacings, so the amount of wet concrete at the middle of the bridge then is different between them. Here you can see about 26.1 at the largest amount, here 21.7, and this is just from different spacing, so each beam is then has its own load and it's taken into account. Here all the construction stages are added, everything is here added within the program, and everything works. So going back to the Excel file, just to make the calculations easier, I changed the amount of elements to 12 just to reduce the runtime within the program. This is then we'll change the vertical value to, vertical curve to 1000 meters. In one of the bridges I had, there was, I think, the smallest radius I've had came into account. This I just added parameter. One can decide to only add 50% of this additional thickness, because it does affect the load bearing capacity of the beams. But thanks to a script like this, you can run it once with 100%, once with 50%, once with 0%, compare the values and see if there are any significant changes just by adding this value. With 1000 meters, you're looking at an extra about 10 centimeters of plate thickness at the center of the pre-stressed beam. So you don't even need to save that file. I'll move this back over here. So once we have all of this, we can then run all of it again. Again, since this wasn't saved, you have the option to save before. It doesn't just automatically override all the work you've done. In this case, we don't want to save what was done before. Here all of the information is being re-exported to the program. First a new file being generated. Once the new file is generated, it starts populating everything. Generally, by adding more elements, the export time doesn't change significantly. As you can see, less dense, the density of the elements between here is a lot smaller. The thickness of this element is not as exaggerated as was before. We have all of the elements been exported. I'll just go back to here. So everything becomes a lot easier. The construction stages are then a simple parameter. So here all of the construction stages, the duration, which elements are activated or deactivated, the time that each stage is activated for, and so on. And here the model is exported, and we have the final model. At this point it's saving the model in this location. It's running the model. I didn't have to do anything, click anything within the program. So theoretically you could run, leave the script overnight and have it run 20, 30, 40 different versions of your bridge, do all the calculations, export all of the important information, and do a separate calculation report for each of the iterations of your bridge. This way you can really optimize your structure, see different versions, expectations from the contractor, and so on. Here just I limited the amount of loads just to decrease runtime, and in a moment when this finishes, I'll just show pulling information out from the program and working on that on the results then thereafter. So here the model is being run. As we can see, here's the amount of time the model has been running. As a side note, one of a nice thing that has been implemented within Civil NX that wasn't in the previous version of Civil is each of the icons here has now its keyboard shortcut, and if you hover over one of the icons when it stops calculating, you could then see what the shortcut is. So now calculation results. If I now run this, so here, run cells in this section, here's an example of getting the data out of MIDAS Civil. This is just an example of node number 1, its coordinates, and these are the coordinates of node number 1. Here I'm pulling out the envelope for the beam stresses and pulling them out and then aggravating them for all of the beams at once. And this is the stresses within the beam, SLS stresses. As we can see here, 0, negative is compression, positive is tension. As we can see at the center point for the blue at the bottom, there are certain load cases where we get high tension values. We have to either increase the amount of tendons or change the layout, or better define the situation, and then we can see what's happening near the center line of the bridge. And going back, with beam design, plate forces, one of the good things about the API is it's not limited to just models that have been created. This can be also used to develop tools for models that have already been calculated. So for example, within an office you could have a standard layout set of load combinations, naming, standardization, and then it's very easy to develop tools that communicate directly to MIDAS Civil, import all the information from there, and do some extra work or combinations or pulling out of various values. So here as an example for slab design, one of the good things is that once doing this, the generation of tables, as we have seen in MIDAS Civil NX, has been the envelope tables have been significantly increased. The time has been shortened, so it's a lot more efficient for pulling out the values. But the nice thing is here we can now create a loop and pull out various tables at once. The downside of doing it in MIDAS Civil, a very small downside, is you have to click through each time, and there's a certain, let's just say, overhead for actually having to do all the things. If you do a loop, you can do various loops all at once. So here for the slab design, here pulling out all the results for the plate forces, run cells in this section, sorry. I'm mentioning run cells. So here it starts pulling out all the values. Here the structure is divided. I divided into groups. So any group that's name starts with RCS, for that group of elements, all the values are then pulled out, and then the tool for slab design then runs for them. So here I have the last crossbeam, the deck above the within the first span, the intermediate crossbeam, here extended a lot longer. It can be of course shorter, the second span, and the last crossbeam. Then for each of these elements, a report is the calculations are done for all the values. Here we can see for the first crossbeam, all of the values have been pulled out and saved to file. Here for the first span, in a moment it will be for the intermediate support, the second span, and the last crossbeam. As we can see, everything is working nicely here. The communication is going between the programs. when it comes to comparing the time that is required to pull the values through the API or directly within the program, it's exactly the same. There's no difference within the actual calculations themselves. It's just we don't have to go through clicking and repeating and doing all of the repeat steps of saving all the values. In a moment we'll have all the values here. This will be slightly exaggerated for the total runtime, but that's just a simplification. Here, as we can see, 3 elements have been exported, and in a moment we'll have the last 2. For just to decrease runtime, in the next stage, the RC slab design, I'll only be doing it for the first span here, the deck in the first span. There's no point in waiting for all of the values to be pulled from the program back into the script here. In a moment this will finish. This will be going on. As a side note, the help files available for the API are, there's a lot of information. It's not a new tool that is only waiting to be developed and explained and everything. The details on the help pages for MIDAS Civil are very extensive, very helpful. Also, contact with MIDAS IT has been very great. They've provided a lot of help with all of the files. In a moment this should finish, and we can carry on to processing the results. Here are all the elements. The last span, I was clicking around, so it looks like it went slightly longer, and the last element done. So and then RC slab design, the plate forces, and then here if I run RC slab design, here it starts running the analysis for the first span, so the elements shown here in red. The calculation for this is takes about a minute. This is just a warning for one of the in one of the points in one of the load cases. This is done. This is of course all of the results that have been pulled out are for all of the ULS and SLS load cases, and then this design is done for both ULS and SLS checks, so that includes cracking width and all the other requirements required here. For this element, there are quite a few nodes, so this is mostly dependent on the amount of nodes and the amount of load cases used. This should be done in a moment. And then once this is done, you have all of the results, and you can check which areas, which regions require what amounts of reinforcement. And just to make this a little bit easier, okay, here are the results. So these are the results. All of the results are generated in 2 versions, so a small picture that is easy to add for a calculation report. So this is the top reinforcement in direction 1, so direction 1 along the length of the bridge. Direction 2 is perpendicular at the top, and then the bottom reinforcement along the length and perpendicular, and then required shear reinforcement just at a certain point is required, and then in a large detail to see the required reinforcement area. So this is along the length again. Here only the maximum value is displayed, but there's the option to have for every point the value shown. So here essentially in this area just the minimal amount of reinforcement is required, due to these sections generally being in compression. and these sections slowly going into tension as we approach the intermediate support. And this is the amount of rebar in the horizontal section. Here we can quite well see the area where we have the live loads, the roadway. Here's the pedestrian area. There's no pedestrian on this pedestrian area on this side, and all of this is done with the built-in load optimization of the lanes. And essentially, with me talking and doing all of this stuff, these calculations were done in about 15 minutes. Of course, this would run faster if I wouldn't explain and have to click through all these things. All of this could be run at once. All of this is run in about 5 minutes if it's done all at once. Of course, you then have to calculate all the other elements, see all the other requirements for the beam, and so on. So going back to the presentation, as an example, so here's the site where all the API manuals are. All the information is there. There are examples of how to use the various functions, how the JSON script should be formatted, what the commands require, what inputs are optional and required, examples of use of the code, and everything is there. And now to finish up slowly, the future development for this tool essentially was to complete the calculation report, so to fully automate the calculation report now, which not much is left as most of the important tools are developed. An extra simple report for each of the bearings, another simplified report, most probably just to have a summary of all the requirements as a yes-no requirements, to have a simple overview of all the requirements, and then exporting the model to MIDAS Sim. Most of the information of the geometry is there, so moving to the next step would be relatively simple. Basically, as a summary, the MIDAS customer support was really helpful here. I had some minor issues. They helped me find the issues, find solutions, and quickly move forward with the project. Thank you very much, and thank you for your time.